Hi, today we're going to be solving some extra problems on filters. So the first one that we're going to do is this circuit right here, and we have a couple of goals for this. So this is going to be the complete run through of all the different things you might have to do with this kind of filter, besides possibly 3 dB frequencies for now. But we will do some examples of that in some of the later examples. So let's see how many we can get to. Determine which type of filter it is by inspection. Find its transfer function. So how we get from the start to the end here. What the voltage at B is relative to the voltage at A in phasor notation. Determine what its gain limits to at high and low frequencies. Determine the frequency that maximizes the gain, which might be infinite or 0, and then the gain at that frequency. And then if the output were instead at point C relative to ground, what type of filter would it be now, and explain. Okay. So the first task is to find the type of filter by inspection. And for this, we're going to be considering what goes on at really high and low frequencies, and then if we have any sort of resonance effect somewhere in the middle. So the key is the inductor and capacitor in relation to where the resistors are positioned. So at really low frequency, we know the capacitor is going to act like an open and the inductor is going to act like a short. And at really high frequencies, the opposite happens. The inductor acts like an open circuit and the capacitor acts like a short. So this is basically a voltage divider network from the elements here, all combined together. So that would be these two in series, 147 in parallel with 100. Maybe together that's something like 67 ohms or so. And then we've got the inductor up here with a 1 ohm, which is going to be a small impedance. So for most of the time you can basically ignore that. And the 1 microfarad capacitor in parallel with that. So that's an inductor in parallel with a capacitor. And you know that acts like a short at extremely low frequencies because of the inductor's effect, and acts like a short at extremely high frequencies because of what the capacitor does. So this thing is something that shorts out from A to B at really low or really high frequencies, but somewhere in the middle, the inductor and the capacitor cancel to create an open circuit. Almost. The resistor gets in the way of that a little bit, so this doesn't quite create an open circuit perfectly like it would if it was just a capacitor and inductor, and it also doesn't quite limit to 0 impedance at extremely low frequencies because of the 1 ohm resistor, but compared to the other resistors in here, it's almost 0. So then what this acts as is an open circuit somewhere in the middle and short circuits at the extremes of frequencies. So then think about how that is going to affect a voltage divider. If the top network of the voltage divider goes to 0 impedance compared to the bottom, then we've got a gain of close to 1 because we're going to have this impedance divided by this plus this one. And if this is 0, then that is just going to equal 1. So at extremely high and low frequencies, we've got a gain of 1. Whereas somewhere in the middle, we've got near infinite impedance here, and that's going to mean we've got this impedance divided by this impedance plus infinity. So that means we're going to have 0. So this is a notch filter for those reasons. So basically, to summarize that, since the LC in parallel has 0 impedance at extremely high or low frequencies, and I guess we'll say nearly 0 because of the resistor throwing things off a little bit. So it's not quite just a perfect LC in parallel, but it's going to be almost like this, and infinite impedance at resonance. So now let's go about finding the transfer function. For this, I'm going to make some definitions to make it a little bit easier. So first, let's define Z top as the impedance of this top branch right there. So that's going to be ZL plus R4 in parallel with ZC. And we're also going to define R bottom as R3 in parallel with R2 plus R1. So then the transfer function H is going to be equal to, by its definition here, voltage at B divided by voltage in, which is actually the voltage at A. So we've got, by a voltage divider, it's going to be the resistance of that bottom network divided by R bot plus Z top. Okay, so substituting in what we found there, we could work out those a little bit more maybe. R bot is just going to be one single resistor after we combine that, so there's not really a huge point in simplifying that further and then substituting in, but we might figure out the frequency dependence of this Z top term and then substitute that into the transfer function to figure out what's going on a little bit intuitively there. So ZL plus R4 in parallel with ZC is, let's see, ZL would be J omega L, and R4, we'll just leave that like that. I guess we could sub in that that's 1 ohm. And then we'll put that in parallel with ZC, which is 1 over J omega C. Okay, so then these two things in parallel are going to be adding up to 1 over the first thing plus 1 over the second thing. So 1 over J omega L plus 1 plus J omega C. Okay. All right, so now we can go and substitute this top impedance into the total transfer function down there. But before we do that, actually I think it's going to be a good idea to clean this up a little bit further. So let's just multiply numerator and denominator by J omega L plus 1 ohm. And then we've got 1 plus the J omega C times that thing. J omega L plus 1 ohm, and that's going to lead us to J omega L plus 1 ohm over 1 plus, and combining those two things, we're going to have a J squared, so that's minus omega squared LC, and then we're left with a plus 1 ohm J omega C. Yeah, that's good. So we'll just write that like that, and then we'll get that ready to substitute in here. So this is going to be equal to R bot over R bot plus that thing. And now we can again multiply numerator and denominator by this factor to clean that up and get rid of the fractions and fractions. So that's going to lead us to that on the top there, and then that on the bottom. And then what we want to do is collect the real and the imaginary parts. Now, you might be tempted to just say, oh, 1 ohm, that's basically 1. Let's just stop writing the ohm symbol. But this is going to be better for understanding what's going on in the circuit later, so we can kind of track down the effect of that 1 ohm impedance, 1 ohm resistor being there, and look at how, and then directly kind of set that to 0 to see how things would be different. And that's going to be useful for understanding what's going on in this problem. So let's sort of multiply this R bottom through here and then take out this term. So we're going to be adding that thing times R bot there. And then we'll take this factor and put it over there with the real stuff on the left, and then maybe factor out a J omega from this imaginary stuff there. So that means we're going to have that. Okay, so now let's analyze what we've got here. First of all, at extremely high frequency and extremely low frequency, we said the transfer function should go to basically 100%. So let's check that. When omega goes to really high values, the omega squared term in numerator and denominator dominates, and then we've got the same value in numerator and denominator. So it's going to limit to negative r bot LC in both of those parts in numerator and denominator. So that means we're going to get a transfer function of 1. At really low frequency, when the inductor is shorting things out and we've got a 1 ohm resistor there, we should also get to basically a transfer function of 1, but maybe modified by that 1 ohm resistor. So when omega goes to 0, then we're left with only r bottom times 1 in the numerator and r bottom times 1 plus 1 ohm in the denominator. So that's just a voltage divider between this thing and the 1 ohm resistor that's left, and that makes sense too. Now at resonance, that's the point where this 1 minus omega squared LC term goes to 0, and we were supposed to, if the 1 ohm resistor is ignorable, go to a transfer function of 0. And you can sort of see that right here. If we were to set this to 0, if this was 0 instead of 1 ohm, then we'd have 0 in the numerator and 0 plus something else, plus not 0, this j omega L term would still be there. So we'd be going to 0 over something, which means we'd get a transfer function of 0. The effect of the 1 ohm resistor is that we don't quite go to 0. Instead, we've got a limit of r bottom times this thing divided by 1 plus j omega L plus r bottom times 1 ohm j omega C. So actually that's the same term as in the numerator. So at resonance, the transfer function goes down to not quite 0, but r bottom times this thing over 1 plus j omega L plus r bottom times the same thing again. So how low we're able to get depends on this 1 ohm times C times r bottom compared to this extra 1 ohm factor, which we can probably ignore, and L, right? So if ignoring this part of the term, if L is, let's say, much larger than 1 ohm times r bottom times C, then we're going to end up with a transfer function that goes basically to 0. But if L is much smaller than that stuff, then the transfer function is not quite going to go to 0. So if you were to replace this instead of with a 1 ohm with like a 400 ohm or something, then we'd have something which is going a lot less to 0 as a transfer function in the middle there. Okay, so that's basically what we expect for this, and that's the analytical confirmation of the transfer function. So the next things that we want to do are determine what the gain limits to at high and low frequencies, the frequency that maximizes the gain and the gain at that frequency, and if the output were instead at point C relative to ground, what filter would this be now, and explain. Okay, so first let's figure out the gain at high and low frequencies. So H at infinity is going to be going to, as we talked through just a moment ago, negative LC times R bottom over negative LC times R bottom, which is going to equal 1. H at 0 is going to be equaling R bottom over R bottom plus 1 ohm, which is, you know, close to 1. It's approximately equal to 1, but not quite. And that's our gain at high and low frequencies. At the maximum, so the frequency that maximizes gain and the gain at that frequency. Now this is hard to do perfectly because of this 1 ohm, but we can say the frequency that maximizes gain will be close to omega equals 1 over root LC, where h at 1 over root LC is the same thing, but with this term going to 0. So then just to substitute in what we found earlier, we've got this expression, which is not quite 0. Oh, you know what? Hold on, I'm answering the wrong question here. This is actually the frequency which minimizes gain, right? So that's sort of an aside. It's not exactly what was asked in this one. So the frequency that maximizes gain is infinite, right? Max gain is 1. We don't have anything in here that can make the output higher voltage than the input. So there's no way we're going to have higher than a gain of 1, which is 100% transferring of the input to the output. So this is basically where you'd get to the frequency that minimizes gain and what the minimum gain is. And again, that's an approximation. The actual one is going to be close to this, but not quite from the 1 ohm impedance. And when we substitute in the numbers, we can look at this in a little bit more detail. Now, the last part is if the output were instead at point C relative to ground, what type of filter would this be now? And what that would do is once we found the output at B, we can then say that, hey, we're just going to do a voltage divider between these two resistors to figure out the output at C instead. So let's maybe give that the symbol for the output at C instead of B. The transfer function would be HC equals the original H multiplied by 100 over 147, I think. Yeah, 100 over 147. So just maybe I'll clarify that this is from a voltage divider. R1 over R1 plus R2. And so all it's going to do is scale all of the gain factors down by close to 33%. So that means this is the same type of filter, a notch filter, but with a lower gain at all frequencies. Yeah. All right, great. So that's the analytical work without substituting in the actual numbers. And next we can substitute in the numbers and confirm this using a computer algebra system, and then even look at Multisim to see if we can confirm these results as well. Okay, so analytical for this circuit in particular, substituting in the numbers here, we can say that R bot is equal to 1 over 100 plus 1 over 147, and there's our bottom. And with Maple, if you put something in as a decimal number, then it'll force the fractional calculation there, so close to 60 ohms. That's about what we were saying. And the Z top is going to be based on those different impedances. So L is equal to 0.1, C is equal to 1 e minus 6, and then we're going to say that we've got Z top is equal to 1 over J, oh, not J, I is our imaginary number in Maple, times omega times C plus 1 over 1 for the R4 plus 1 over I times omega times L. Okay. So Z top should be equal to this, and maybe we can simplify that to see if it gets closer to the form that we were expecting for that impedance. And this is a little bit strange because we expected that 1 ohm term there. You know, okay, so they're not all in parallel. It's the inductor in series with the 1 ohm. So it's actually like that. Okay, that makes more sense. Now we've got the right kind of expression where we still have that real part in the numerator, just like we found analytically. Okay, so, I mean, remember that just because a computer algebra system has, 16, 18 decimals of precision doesn't mean it's always right. It can only do what you tell it to do, which is the biggest disadvantage of these systems. They always do what you tell them. So it's kind of on you to tell them the right thing. Now, the next part is to figure out the transfer function. So h is going to be equal to the r bot divided by r bot plus z top. And there's that. We can simplify that and get an expression which should have the same form as we calculated. So let's see. We've got something times a negative omega squared, and there's a constant there as well, and then an imaginary part, and then similar form in the denominator. Negative omega squared and some constants, and then an imaginary part times omega. Okay, now we can look for what this is limiting to in terms of magnitude and phase. Let's plot the abs of h from omega is equal to, let's say, 1 to 1e6, just to start exploring around. Okay, and to see this a bit better, let's turn on advanced plots and do a semilog plot. Aha, notch filter. Now, in the semilog plot, it doesn't show. It sort of picks the points linearly. So there's a lot more points up here than there are on the other side. We can fix this by just adding in more points. There's smarter ways to fix it, but this will be okay for now. And there we go. So we've got a notch filter, and it looks like the frequency that it notches at is close to so 10 to the 3. So there's 1,000. There's 10,000. So how many different intervals do we have here? Not quite all 10 different divisions. So a little bit tough to see what's going on here. But if you look at the top, Maple is telling you what we're close to there. So that's like 3,200, maybe 3,000 for the frequency there. Okay, and that is probably pretty close to our 1 over square root LC. Yeah, so 3,200 is what we had. I mean, that's not a new thing. This is actually the same capacitor and inductor value that we were using in the last problem, and that's because these are the ones that we've got in the lab. So the 3,200 is what you'd expect for the omega, and you may remember that the cyclical frequency that corresponds to is about 503, I think. So this is this thing divided by 2 times 3.14159, and we've got, 503 hertz that this corresponds to. Okay, now notice also that the gain does limit to nearly 1 at the high and low frequency ends, and it does go down to close to 0 right here in the middle, and that is pretty close to our 1 over root LC as expected. Okay, so that's the confirmation using a computer algebra system. Now we can go on and do this with Multisim. So we've got the circuit built here, and we can add in our Bode plotter tool here to look at what the transfer function is kind of directly. So let's wire that up. B versus ground and give it a shot. All right, so we've got a notch there. Let's put the frequency around the right kind of range. So we expect it's going to be close to 500 hertz. So let's go up to 1K and up from 200. Yeah, so it looks like we've got something that's pretty close to 500 there. Yeah, 502 is seeming like the limit there. I wonder if we can put in an arbitrary value. So let's try 450. Oh yeah. And maybe 500, and let's go to 505. 495. 490. Seems like it's a little bit lower. So 475. 450. Yeah. And 460 hertz. Oh, maybe that just wasn't updating. .500 hertz, and we'll go up to 505 hertz. Now it's sort of hard to see, but you can see there's a minimum right there at, looks like between 501 and 502. Then we can raise that up and see how low we're getting in terms of the minimum. So we might now actually expand that out in either direction. Yeah. So from towards 0 decibels at the ends, you'd expect, and then right in the middle we've got a notch which is going down to a pretty low frequency. So this is actually, despite the 1 ohm resistor being there, getting us pretty close to 0. Let's expand this further, and you see as we get far enough away, then we do limit to a gain of 1, which is limiting to 0 decibels there. Let's go up to the gigahertz. And yeah, so we're basically going to 1 at high frequencies, and then let's maybe go back to the millihertz there on the other end, and gain of 1 at low frequencies too. So there's the confirmation of this acting as a notch filter and behaving the same as we expected. So the last thing you might want to do is kind of confirm that the output being at point C instead doesn't actually change anything about what's going on with the filter except for the gain. So you expect the whole thing to just shift down a little bit, but besides that it should be the same. And there it is. Great. So that's it for this question. Thanks for watching.